We're going to be looking at linear elastic deformation. And so first, what we mean by elastic is just that when we load a sample up, so this is my stress strain data, say taken on that tensile machine, I could, instead of running this to failure like you saw, we could stop after some load, some stress value, and unload, and we would end up back at 0. And that's the definition of elastic. We would return to our original shape. There's no permanent deformation in this case. We're only stretching bonds. And in many material systems, this early region, this initial region of the stress strain curve is also linear. So under those conditions, then we can simply take the slope of this linear region and define that as our elastic modulus, or Young's modulus is also another way of referring to this value. Okay. That typically has some units of like gigapascals for metals, maybe megapascals for polymers. And so if we just rearrange this equation and we have stress is equal to this elastic modulus times strain, then we have what's called Hooke's law. Okay. This elastic modulus is a material property. Right? So notice how our definition of stress and strain allowed us to take the dimensions out of the sample, and so that we had a material property that's independent of sample dimensions. If we left it as a force equal to K times, instead of strain, now just a position, displacement of our sample, we would have what we're used to from physics for a spring, where K would be the spring stiffness. But now if I was to increase the area of my sample, then in order to get the same displacement X, I would need to pick up the force. Otherwise, the stiffness would go up. This is dependent upon geometry. So this is why we don't use this form, but we put it into stress and strain and use Hooke's law. For shear, we have the shear modulus, shear stress, and shear strain, which we just saw recently defined. All right, for some materials, the initial region is no longer linear. That's the example of a cast iron. So a cast iron, if you were to unload at some point, it will return. It may have some hysteresis, but it will generally follow this curve and it will return to 0 strain. And so we will recover all of the strains put into the sample, and hence it's elastic. But you can clearly see that it's not linear. So we can't define the elastic modulus like we did previously because we don't have a linear region. So what we could do is either define something like a secant modulus. So we just draw a straight line from the origin here up to some value, and we pull off the slope of that. And that would be referred to as a secant modulus at sigma 1. Or we could pick some value here, sigma 2, and then we could just define the tangent at that point. And that would also, of course, be a stress over strain. So this is referred to as a tangent modulus. With these, we do have to define these sigma values of where the measurement was taken from. Right. So that's their example of cast iron. And we'll take a look at some real data in a couple of videos from now, showing you the actual form of cast iron. But this is referred to again as nonlinear elastic deformation. All right, so next time we're going to go ahead and take a look at the bonding again that we did in chapter 2, and we'll see how this is related to the elastic modulus.